Hello, and welcome to Organic Chemistry with Crip. This video will focus on different trends, bond energy, and also refer to conjugation as well as hyperconjugation. We begin at the top left, and you notice here with a series of single bonds between our second energy level elements. Notice how the carbon single bonded to carbon bond is actually substantially stronger than the nitrogen single bonded nitrogen, oxygen single bonded oxygen, and fluorine single bonded fluorine. This might go against what you would expect in terms of trends. Perhaps you would expect that increased electronegativity would mean that the bond should get stronger. And that's right. With increased electronegativity, we should see a greater stabilization of electrons. But because the carbon single bonded carbon is associated with no unshared pairs on that central carbon, because of that, and because once we start single bonding the nitrogen, oxygen, or fluorine, where we will have unshared pairs adjacent to that bond, we clearly see that the presence of nearby adjacent unshared pairs on that atom will actually increase that energy of the single bond. It is important at this juncture to remind you what a bond is formed of. A bond is just an overall attraction of electrons right between two nuclei. If the atoms are completely separate, so on our graph that would be to the right of this graph, there would be no attraction and no repulsion. But as the atoms get closer, attraction increases until we get to the most attracted state, which is associated with that bond distance, and the lowest potential energy state on our graph. If we were to push the electrons toward each other even more, we see that repulsions increase. And that is essentially how we would break a chemical bond. Some energy would need to come in to a system for a collision. It would have to squish the atoms into each other. The electrons in the bonding molecular orbital would transition to an anti-bonding state, and then there would be increased repulsions, and in the next movement, the bond would snap away from each other. So it is important to keep this dynamic in your mind. With this dynamic in mind, when we look at this chart, we can see that more repulsive groups will raise the energy of the electrons, and the bond, the attraction, will be easier to break. Remember, bond energy is the kinetic energy required. It is not referring to the potential energy state. So if the potential energy of the electrons are lower, like in the carbon single bonded carbon that requires 347, it's going to require more energy to break that bond, to remove those electrons. I'm saying removing because you probably saw this dynamic with ionization energy. That's the last time you were rationalizing these dynamics. So carbon single bonded carbon is actually really strong bond, and it's important to note that relative to other single bonds. Now, if we compare carbon single bonded carbon to carbon double bonded carbon to carbon triple bonded carbon, we see that the hybridization of carbon single bonded carbon is sp3 hybridized versus the carbon double bond is sp2, and the triple bond sp. With greater s character, the bonds will get smaller. The hybridization is becoming having more s character. These bonds are getting stronger. Therefore, the overall effect is that the bond energy will increase because the electrons are more attracted. Compare the carbon single bonded to nitrogen compared to the carbon double bonded to nitrogen, compared to the carbon triple bonded to nitrogen, compared to the carbon triple bonded to nitrogen with a negative charge on the carbon. You can see the dynamic is with more bonds, the energy of the electrons increases. Same thing with carbon bonded to oxygen. You can see that dynamic as well. Notice how having the carbon with a negative charge increases the electrons just a little bit in the cyanide ion, but because you have opposite charges in carbon monoxide, the energy is slightly higher. And you can see also the dynamic at work in nitrogen single bonded to nitrogen versus nitrogen double bonded to nitrogen and nitrogen triple bonded to nitrogen. Same thing with oxygen as well. So more bonding, right, will be associated with hybridized states that have more S character, which will mean that the bond becomes smaller in size and the sigma bonds and pi bonds get more attracted through that dynamic. And it's not just those bonds themselves, the single to double to triple inside. Again, when you change the S character, when we go from sp3 hybridized carbon single bonded to hydrogen to sp2 hybridized carbon single bonded to hydrogen compared to sp hybridized carbon single bonded to hydrogen, again, the bond energies will increase due to greater S character, due to those atoms being more strongly attracted to the electrons between them because they're becoming smaller in size due to that greater S character in the hybridized state for carbon. Furthermore, compare some nonmetal single bonded to hydrogen. And here we have another kind of periodic trend effect. If you recall with periodic trends, there was this quote unquote exception to the periodic trends when you get to groups that start to have electron pairing. Here we can see there is a drop in bond energy due to the beginning of unshared pairs being adjacent to that single bond. You can compare carbon single bonded to hydrogen, 413 kilojoules per mole, and then it drops with nitrogen single bonded to hydrogen, 391, and then it increases again because with greater electronegativity will stabilize those electrons from hydrogen. So now it goes up again, 463, and then finally 567. Right? You can see also as we get larger in size, larger in atomic size, and not as electronegative, we can see also the trend as being decreasing that bond energy with reference to the, in comparison to the smaller second energy level elements. For those of you who may need a little refresher on periodic trends, I've included the electron configurations for the first 18 or so elements here. And remember, this is a dynamic picture. You may have seen diagrams before where you represent electrons with arrows and the boxes would represent orbitals. Unfortunately, that picture many times is very static. It's not dynamic. It is important to note that as you increase the number of protons, the electron energies will be shifted downward. So that's why you see this overall truer effect in which the electrons are shifted in downward, more attracted to the nucleus. But as you increase in energy level or sublevel, because the lower energy electrons are repelling these higher energy electrons into that state, what we see is that overall effect, right? As we increase in energy level or sublevel or pairing. So if you look carefully for, let's say, oxygen compared to nitrogen, you will see that the paired state puts those electrons at a higher energy state versus the unpaired state. Same thing with sulfur with reference to phosphorus, and you can see that later on in the graph. Again, it is the electron-electron pairing which generates more repulsions, which raises the potential energy of those electrons, and that's why they don't require as much energy to be ionized. So that dynamic with atomic orbitals is exactly the same dynamic with molecular orbitals. We have essentially the same type of trend. It's just located a little bit differently. And so you can see in the lower right hand graph, now we've got a carbon single bonded to all of these other nonmetals. So you can see carbon single bonded to carbon, and then below it, silicon single bonded to carbon. And that's a methyl group. So nitrogen would be single bonded to carbon, and that carbon would be bonded to 3 other hydrogens, right? And so this is using our representation from skeletal structures. But we see exactly the same dynamic at work that we see when those nonmetals were single bonded to hydrogen. As we go across the period, due to greater electronegativity, due to a greater attraction of those electrons, we see bond energies generally increase. But we see this quote unquote exception to that trend with the introduction of electron-electron pairing, which raises the total energy state of all the electrons around it. So to summarize, we've got some interesting dynamics at work here. And you really should kind of put this as a accessible chart somewhere. We've already discussed that sigma bonds would be the most attracted state in terms of comparing bonds or unshared pairs. Sigma bonds have no angular nodes, no planar nodes, right? And so those are 2 nuclei attracting electrons between them, versus the pi bonds. Pi bonds will be associated with 1 angular node and are of higher in energy, but by virtue of being attracted, they are still more stable compared to unshared pairs or non-bonding pairs that are only attracted to 1 nucleus. Conversely, if you have a greater positive formal charge on an atom, those electrons around it will be much more attracted to that nucleus, versus greater negative charge implies higher electron density, and therefore those electrons are going to be more repelled in an overall higher energy state. Overall, if we're comparing all things equal, more electronegativity will be associated with greater attraction. And so definitely comparing carbon compared to nitrogen, compared to oxygen, compared to fluorine. And specifically, if we were to make the comparison an unshared pair, unshared pairs on carbon compared to nitrogen, compared to oxygen, compared to fluorine, they, again, all other things being equal, meaning they have the same formal charge, then those unshared pairs or bonding pairs will be more attracted to the electronegative atom. And again, the comparison requires all other things being equal. And that's why we didn't see that dynamic when we had, say, all single bonds and then, introduction of single bonds and there's an adjacent unshared pair. It really is important that all other dynamics surrounding that nucleus are equal. Conversely, as if we were to say unshared pairs on a halogen going down the group, because the atoms are getting larger and larger in size, it's going to be associated with less repulsions. And so those unshared pairs won't nearly be as reactive because they're really being distributed around that much larger atom. Also noting hybridization, which we've touched on. The 3 key hybridization states for second energy level elements, of course, are going to be sp, sp2, sp3, and greater s character will always be associated with an intensely more attracted state. This leaves 2 or 3 other dynamics that we want to refer to at the rest of this video in relation to conjugated and hyperconjugated orbitals. Now, resonance structures are something that you have encountered in general chemistry, but resonance structures are going to generally be associated with more attraction. You have to think that if a charge is localized in one location on one nucleus, then especially negative charge is going to be way more reactive. And so negative charge stabilized by resonance, or in terms of, we'll get to positive charge as in a lack of electrons. But anytime you have a conjugation of p orbitals in which this pi molecular orbital is actually stabilized stabilized by being associated with multiple resonance structures. We call this that those p orbitals that are used to form that pi bond, that they are conjugated. So if you notice the graph to the right, the pi molecular orbital really is associated with being delocalized across those three p orbitals. Same thing with the dynamic in the enolate ion at the bottom. Here at the carboxylate ion, I have it associated with two bonds that are kind of equal status. They're equal resonance contributors, versus the ones associated with the ones below are associated with a minor resonance contributor, a less stable state, and a more stable state, the major resonance contributor. However, still the effect is such that the p orbitals that make up that pi molecular orbital are conjugated. And although the pi bond is just weakened a little bit, overall it has the effect of attracting the sigma bonds even more. And remember, it's going to be associated with a hybridization in which those hybridized states are actually have more S characters, so therefore more attracted. So overall, the function of resonance structures is really to be associated with these conjugated p orbitals that will, again, generally stabilize, make the electrons more attracted in this state. But resonance is only one type of electron delocalization. So the electron delocalization with resonance structures is associated with a conjugated p orbitals and that delocalized pi bond. But we can also have a delocalization associated with sigma bonds. And this helps us to understand why different carbocations, why a primary carbocation would be extremely reactive, more reactive compared to a secondary carbocation, and compared to a tertiary. Tertiary would be substantially more stable. And that's because with greater electron density around that positive charge, what you will see is you will have sigma bonds, more sigma bonds that are able to be lined up with that empty p orbital. And so that empty p orbital can attract and sync up constructively with those adjacent sigma bonds, and those adjacent sigma bonds would be more attracted to that empty p orbital, and so they would be what we call hyperconjugated. The sigma molecular orbitals would be hyperconjugated with the adjacent empty p orbital, and the more sigma molecular orbitals that you have with an adjacent empty p orbital, the more stable, the more attracted that state will be. So clearly, if we have more sigma bonds next to this adjacent empty p orbital, so if you have a tertiary carbocation, that's going to have more attraction than a secondary carbocation or a primary carbocation. But the opposite, the effect is opposite if we're talking about carboanions. Here, with a carboanion, we actually have that p orbital filled. So more adjacent sigma molecular orbitals will actually raise the energy state of that negative charge, because you've got more electron domains, more sigma orbitals adjacent, means that there will be more possible repulsions. So notice that in that case, the tertiary carbanion, the tertiary carbanion, is actually the highest energy state, more repelled than a secondary carbanion and primary carbanion. And with those dynamics, that wraps up this video on bond energy trends. Till next time, Crypt.